State machine, an overview. A finite state machine FSM or finite state automaton FSA, plural, automaton. A finite automaton, or simply a state machine, is a mathematical model of computation. It is an abstract machine that can be in exactly one of a finite number of states at any given time. The FSM can change from one state to another in response to some inputs. The change from one state to another is called a transition. An FSM is defined by a list of its states, its initial state, and the inputs that trigger each transition. Finite state machines are two types: deterministic finite state machines and non-deterministic finite state machines. A deterministic finite state machine can be constructed equivalent to any non-deterministic one. The behavior of state machines can be observed in many devices in modern society that perform a predetermined sequence of actions depending on a sequence of events with which they are presented. Simple examples are vending machines, which dispense products when the proper combination of coins is deposited, elevators, whose sequence of stops is determined by the floors requested by riders, traffic lights, which change sequence when cars are waiting, and combination locks, which require the input of a sequence of numbers in the proper order. The finite state machine has less computational power than some other models of computation, such as the Turing machine. The computational power distinction means there are computational tasks that a Turing machine can do but an FSM cannot. This is because its memory is limited by the number of states it has. A finite state machine has the same computational power as a Turing machine that is restricted such that its head may only perform read operations, and always has to move from left to right. This is studied in the more general field of automata theory. Example: coin-operated turnstile. An example of a simple mechanism that can be modeled by a state machine is a turnstile. A turnstile, used to control access to subways and amusement park rides, is a gate with 3 rotating arms at waist height, one across the entry. Initially, the arms are locked, blocking the entry, preventing patrons from passing through. Depositing a coin or token in a slot on the turnstile unlocks the arms, allowing a single customer to push through. After the customer passes through, the arms are locked again until another coin is inserted. Considered as a state machine, the turnstile has 2 possible states, locked and unlocked. There are 2 possible inputs that affect its state: putting a coin in the slot coin and pushing the arm push. In the lock state, pushing on the arm has no effect. No matter how many times the input push is given, it stays in the lock state. Putting a coin in, that is, giving the machine a coin input, shifts the state from locked to unlocked. In the unlocked state, putting additional coins in has no effect. That is, giving additional coin inputs does not change the state. However, a customer pushing through the arms, giving a push input, shifts the state back to locked. The turnstile state machine can be represented by a state transition table, showing for each possible state the transitions between them based upon inputs given to the machine and the outputs resulting from each input. The turnstile state machine can also be represented by a directed graph called a state diagram above. Each state is represented by a node circle. Edges arrows show the transitions from one state to another. Each arrow is labeled with the input that triggers that transition. An input that doesn't cause a change of state, such as a coin input in the unlocked state, is represented by a circular arrow returning to the original state. The arrow into the lock node from the black dot indicates it is the initial state. Concept and terminology. A state is a description of the status of a system that is waiting to execute a transition. A transition is a set of actions to be executed when a condition is fulfilled or when an event is received. For example, When using an audio system to listen to the radio, the system is in the radio state. Receiving a next stimulus results in moving to the next station. When the system is in the CD state, the next stimulus results in moving to the next track. Identical stimuli trigger different actions depending on the current state. In some finite state machine representations, it is also possible to associate actions with a state. An entry action performed when entering the state, and an exit action performed when exiting the state. Representations. State event table. Several state transition table types are used. The most common representation is shown below. The combination of current state EGB and input EGY shows the next state EGC. The complete actions information is not directly described in the table and can only be added using footnotes. An FSM definition including the full actions information is possible using state table. See also virtual finite state machine. UML state machines. The Unified Modeling Language has a notation for describing state machines. UML state machines overcome the limitations of traditional finite state machines while retaining their main benefits. UML state machines introduce the new concepts of hierarchically nested states and orthogonal regions, while extending the notion of actions. UML state machines have the characteristics of both Mealy machines and Moore machines. They support actions that depend on both the state of the system and the trigger event, as in Mealy machines, as well as entry and exit actions, which are associated with states rather than transitions, as in Moore machines. STL state machines. The specification and description language is a standard from ITU that includes graphical symbols to describe actions in the transition. Send an event. Receive an event. Start a timer. Cancel a timer. Start another concurrent state machine. Decisions embeds basic data types called abstract data types, an action language, and an execution semantic in order to make the finite state machine executable. Other state diagrams. There are a large number of variants to represent an FSM, such as the one in Figure 3. Usage. In addition to their use in modeling reactive systems presented here, finite state machines are significant in many different areas, including electrical engineering, linguistics, computer science, philosophy, biology, mathematics, video game programming, and logic. Finite state machines are a class of automata studied in automata theory and the theory of computation. In computer science, finite state machines are widely used in modeling of application behavior control theory, design of hardware digital systems, software engineering, compilers, network protocols, and computational linguistics. Classification. Finite state machines can be subdivided into acceptors, classifiers, transducers, and sequencers. Acceptors. Acceptors, also called detectors or recognizers, produce binary output, indicating whether or not the received input is accepted. Each state of an acceptor is either accepting or non-accepting. Once all input has been received, if the current state is an accepting state, the input is accepted, otherwise it is rejected. As a rule, input is a sequence of symbols, characters. Actions are not used. The start state can also be an accepting state, in which case the acceptor accepts the empty string. The example in Figure 4 shows an acceptor that accepts the string is. In this acceptor, the only accepting state is state 7. A possibly infinite set of symbol sequences, called a formal language, is a regular language if there is some acceptor that accepts exactly that set. For example, the set of binary strings with an even number of zeros is a regular language. Fig. 5. While the set of all strings whose length is a prime number is not. 71. An acceptor could also be described as defining a language that would contain every string accepted by the acceptor but none of the rejected ones. That language is accepted by the acceptor. By definition, the languages accepted by acceptors are the regular languages. The problem of determining the language accepted by a given acceptor is an instance of the algebraic path problem. It's also a generalization of the shortest path problem to graphs with edges weighted by the elements of an arbitrary semi. An example of an accepting state appears in Fig. 5. A deterministic finite automaton DFA that detects whether the binary input string contains an even number of which is also the start state, indicates the state at which an even number has been input. This is therefore an accepting state. This acceptor will finish in an accept state if the binary string contains an even number, including any binary string containing no's. Examples of strings accepted by this accept are the empty string 1, 11, 11, 0, 10, 10, 10, 10,000, 110, etc. Classifiers. Classifiers are a generalization of acceptors that produce an area output where n is strictly greater than 2. Transducers. Transducers produce output based on a given input under a state using actions. They are used for control applications and in the field of computational linguistics. In control applications, two types are distinguished. Mir machine. The FSM uses only entry actions, i.e., output depends only on state. The advantage of the Mir model is a simplification of the behavior. Consider an elevator door. The state machine recognizes two commands, command open and command close, which trigger state changes. The entry action in state opening starts a motor opening the door. The entry action in state closing starts a motor in the other direction closing the door. States opened and closed stop the motor when fully opened or closed. They signal to the outside world, e.g., to other state machines the situation, door is open or door is closed on melee machine. The FSM also uses input actions, i.e., output depends on input and state. The use of a melee FSM leads often to a reduction of the number of states. The example in Figure 7 shows a melee FSM implementing the same behavior as in the Mir example. The behavior depends on the implemented FSM execution model and will work, e.g., for virtual FSM but not for event-driven FSM. There are two input actions, i.e., start motor to close the door if command close arrives, and start motor in the other direction to open the door if command open arrives. The opening and closing intermediate states are not shown. Sequencers. Sequencers, also called generators, are a subclass of acceptors and transducers that have a single letter input alphabet. They produce only one sequence, which can be seen as an output sequence of acceptor or transducer outputs. Determinism. A further distinction is between deterministic DFA and non-deterministic in FAG and FA automata. In a deterministic automaton, every state has exactly one transition for each possible input. In a non-deterministic automaton, an input can lead to one, more than one, or no transition for a given state. The parasite construction algorithm can transform any non-deterministic automaton into a usually more complex deterministic automaton with identical functionality. A finite state machine with only one state is called a combinatorial FSM. It only allows actions upon transition into a state. This concept is useful in cases where a number of finite state machines are required to work together, and when it is convenient to consider a purely combinatorial part as a form of FSM to suit the design tools. Alternative semantics. There are other sets of semantics available to represent state machines. For example, there are tools for modeling and designing logic for embedded controllers. They combine hierarchical state machines which usually have more than one current state, flow graphs, and truth tables into one language, resulting in a different formalism and set of semantics. These charts, like Carroll's original state machines, support hierarchically nested states, orthogonal regions, state actions, and transition actions. Mathematical model. In accordance with the general classification, the following formal definitions are found. A deterministic finite state machine or deterministic finite state acceptor is a quintuple. 0. As display style sigma is a delta f, where as display style sigma is the input alphabet a finite non-empty set of symbols. As display style s is a finite non-empty set of states. 0. As display style s is an initial state and an element of as display style s. As display style delta is a state transition function. As display style delta is at times sigma iriter s. In a non-deterministic finite automaton it would be as display style delta is at times sigma iriter mascal ips, i.e. as display style delta would return a set of states. As display style f is a set of final states, a possibly empty subset of as display style s. For both deterministic and non-deterministics, it is conventional to allow a display style delta to be a partial function, i.e. a display style delta sexa does not have to be defined for every combination of a display style sin s, add a display style sin sigma. If an FSM a display style m is in a state a display style s, the next symbol is a display style x. Add a display style delta sexa is not defined, then a display style m can announce an error, i.e. reject the input. This is useful in definitions of general state machines, but less useful when transforming the machine. Some algorithms in their default form may require total functions. A finite state machine has the same computational power as a Turing machine that is restricted such that its head may only perform read operations, and always has to move from left to right. That is, each formal language accepted by a finite state machine is accepted by such a kind of restricted Turing machine, and vice versa. A finite state transducer is a sextuple. 0 as display style sigma gamma delta omega, where display style sigma is the input alphabet a finite non-empty set of symbols. Display style gamma is the output alphabet a finite non-empty set of symbols. Display style s is a finite non-empty set of states. 0 display style s is the initial state, an element of display style s. Display style delta is a state transition function. Display style delta is a times sigma iterator s. Display style omega is the output function if the output function depends on the state and input symbol. Display style omega is a times sigma iterator gamma. That definition corresponds to the Mealy model and can be modeled as a Mealy machine if the output function depends only on the state. Display style omega is a iterator gamma. That definition corresponds to the Moore model and can be modeled as a Moore machine. A finite state machine with no output function at all is known as a semi-intermittent or transition system. If we disregard the first output symbol of a Moore machine, 0 display style omega s, then it can be readily converted to an output equivalent Mealy machine by setting the output function of every Mealy transition, i.e. labeling every edge with the output symbol given of the destination Moore state. The converse transformation is less straightforward because a Mealy machine state may have different output labels on its incoming transitions edges. Every such state needs to be split in multiple Moore machine states, one for every incident output symbol. Optimization. Optimizing an FSM means finding a machine with the minimum number of states that performs the same function. The fastest known algorithm doing this is the Hopcroft minimization algorithm. Other techniques include using an implication table or the Moore reduction procedure. Additionally, a cyclic process can be minimized in linear time. Implementation. Hardware applications. In a digital circuit, an FSM may be built using a programmable logic device, a programmable logic controller, logic gates and flip-flops or relays. More specifically, a hardware implementation requires a register to store state variables, a block of combinational logic that determines the state transition, and a second block of combinational logic that determines the output of an FSM. One of the classic hardware implementations is the Richards controller. In a Medvedev machine, the output is directly connected to the state flip-flops, minimizing the time delay between flip-flops, and output for state encoding for low-power state machines may be optimized to minimize power consumption. Software applications. The following concepts are commonly used to build software applications with finite state machines. Automata-based programming. Event-driven finite state machine. Virtual finite state machine. State design pattern. Finite state machines and compilers. Finite automata are often used in the front end of programming language compilers. Such a front end may comprise several finite state machines that implement a lexical analyzer and a parser. Starting from a sequence of characters, the lexical analyzer builds a sequence of language tokens such as reserved words, literals, and identifiers from which the parser builds a syntax tree. The lexical analyzer and the parser handle the regular and context-free parts of the programming language's grammar. Further reading. General. Sakharovich, Jacques 2009. Elements of Automata Theory. Translated from the French by Ruben Thomas. Cambridge University Press. ISBN 978-180-425-3. Full 1188.68177. Webner, F. Modeling Software with Finite State Machines, A Practical Approach, Albach Publications, 2006, ISBN 0-8000-493-8086-3. ITUT, Recommendation, Specification and Description Language STL. Samick, M. Practical Statcharts Inc., CMP Books, 2002. ISBN 157820-110-1. Samick, M. Practical UML Statcharts Inc., 2nd edition, Nunes, 2008, ISBN 07000-506-8706-1. Garner, T. Advanced State Management, 2007. Cassandras, C. La Fortune, S. Introduction to Discrete Event Systems. Kluwer, 1999, ISBN 07923-800694. Timothy Kampf, Synthesis of Finite State Machines, Functional Optimization. Kluwer Academic Publishers, Boston 1997, ISBN 07923-900842-4. Tiziana Villa, Synthesis of Finite State Machines, Logic Optimization. Kluwer Academic Publishers, Boston 1997, ISBN 07093-900892-0. Carol, J. Long, D. Theory of Finite Automata with an Introduction to Formal Languages. Prentice Hall, Englewood Cliffs, 1989. Kohave, C. Switching and Finite Automata Theory. McGraw-Hill, 1978. Gill, A. Introduction to the Theory of Finite State Machines. McGraw-Hill, 1962. Ginsberg, S. An Introduction to Mathematical Machine Theory. Addison Wesley, 1962. Finite State Machines Automata Theory in Theoretical Computer Science. Arbab, Michael, 1969. Theories of Abstract Automata, 1st ed. Englewood Cliffs, N.J., Prentice Hall, Inc. ISBN 978-013-913,368-8. Boborow, Leonard S. Arbab, Michael, 1974. Discrete Mathematics, Applied Algebra for Computer and Information Science First Ed. Philadelphia, W.B. Saunders Company, Inc. ISBN 978-07216-1768-8. Booth, Taylor L. 1967. Sequential Machines and Automata Theory First Ed. New York, John Wiley & Sons, Inc. Library of Congress Card Catalog Number 6725924. Bullis, George, Jeffrey, Richard 1999-1989. Computability and Logic 3rd ed. Cambridge, England, Cambridge University Press. ISBN 978-0520-120,402-6. Brookshire, J. Glenn 1989. Theory of Computation, Formal Languages, Automata, and Complexity. Redwood City, California, Benjamin Cummings Publish Company, Inc. ISBN 978-08053-143-4. Davis, Martin, Seigel, Ron, Ruker, Elaine J. 1994. Computability, Complexity, and Languages and Logic. Fundamentals of Theoretical Computer Science 2nd ed. San Diego, Academic Press, Harcourt, Brace and Company. ISBN 978-012-200-6000-382-4. Hopcroft, John, Ullman, Jeffrey 1979. Introduction to Automata Theory, Languages, and Computation First ed. Reading Maths, Addison Wesley. ISBN 978-020-129-888. Hopcroft, John E. Motany, Rajiv, Ullman, Jeffrey D. 2001. Introduction to Automata Theory, Languages, and Computation 2nd ed. Reading Maths, Addison Wesley. ISBN 978-0-200-144,124-6. Holkin, David, Moss, Barbara 1976. Stomata. New York, Elsevier, North Holland. ISBN 978-0-444-249-5. Curzon, Dexter C. 1997. Automata and Computability First ed. New York, Springer Verlag. ISBN 978-0-387-94,907-9. Lewis, Harry R. Papadimitriou, Christus H. 1998. Elements of the Theory of Computation 2nd ed. Upper Saddle River, New Jersey, Prentice Hall. ISBN 978-013-260-2000-478-7. Linz, Peter 2006. Formal Languages and Automata 4th ed. Selbury, M.A., Jones and Butler. ISBN 978-0-7000-637-3798-6. Minsky, Marvin 1967. Computation, Finite and Infinite Machines First ed. New Jersey, Prentice Hall. Papadimitriou, Christus 1993. Computational Complexity First ed. Addison Wesley. ISBN 978-0-200-153,082-7. Pippinger, Nicholas 1997. Theories of Computability First ed. Cambridge, England, Cambridge University Press. ISBN 978-520-155,383. Roger, Susan, Finley, Thomas 2006. JFLAP, an interactive formal languages and automata package first ed. Selbury, N.A., Jones and Bartlett. ISBN 978-07637 3830 Sepser, Michael 2006. Introduction to the Theory of Computation Second ed. Boston, Mass. Thompson Course Technology. ISBN 978-0534-95097-2. Wood, Derek 1987. Theory of Computation First ed. New York, Harper & Row, Publishers, Inc. ISBN 978-0647-208-5. Abstract State Machines in Theoretical Computer Science. Yurovich, Yuri, July 2000. Sequential Abstract State Machines Capture Sequential Algorithms PDF. ACN Transactions and Computational Logic. 1-1. Sitzers. Doi. C2,031,696. Machine Learning Using Finite State Algorithms. Mitchell, Tom M. 1997. Machine Learning First ed. New York, McGraw-Hill Corporation. ISBN 978-0740-2872. Hardware Engineering State Minimization and Synthesis of Sequential Circuits. Booth, Taylor L. 1967. Sequential Machines and Automata Theory First ed. New York, John Wiley & Sons, Inc. Library of Congress Card Catalog number 6725924. Booth, Taylor L. 1971. Digital Networks and Computer Systems First ed. New York, John Wiley & Sons, Inc. ISBN 978-0471-8840. Klusky, E.J. 1965. Introduction to the Theory of Switching Circuits First ed. New York, McGraw-Hill Book Company, Inc. Library of Congress Card Catalog number 6517394. Hill, Frederick J. Peterson, Gerald 1965. Introduction to the Theory of Switching Circuits First ed. New York, McGraw-Hill Book Company. Library of Congress Card Catalog number 6517394. Finite Markov chain processes. We may think of a Markov chain as a process that moves successively through a set of states. Senior. If it is in state C, it moves on to the next stop to states with probability pi. These probabilities can be exhibited in the form of a transition matrix. Kemeny 1959. Finite Markov chain processes are also known as subsets of finite type. Booth, Taylor L. 1967. Sequential Machines and Automata Theory First ed. New York, John Wiley & Sons, Inc. Library of Congress Card Catalog number 6725924. Kemeny, John G. Merkel, Hazelton, Snell, J. Laurie, Thompson, Gerald L. 1959. Finite Mathematical Structures First ed. Englewood Cliffs, N.J. Prentice Hall, Inc. Library of Congress Cod Catalog number 59 12841. Chapter 6 Finite Markov Chains. Thank you for watching a video on State Machine, brought to you by Dick Kurific. Don't forget to like and subscribe. Bye for now.